This is the, I think probably the third or fourth discussion of virtual memory as we go through this. And last time we started talking about page replacement policies. So we introduced the notion and also some of the very basic concepts. We talked about this really simple policy called FIFO. Let me see what I have here. Yeah, so there's a FIFO, and basically it works just like you would expect. Yes, CS124 botulism. So prog powder, really cool if you ever want to get into making bacon or anything like that. Literally, not figuratively. So yeah, but you put the pages on the end of a FIFO queue and they slowly make their way to the front, and whenever you need to evict a page, you just take the page off the front of the FIFO and that's your eviction page. So doesn't really take access into account. It just uses this when things are accessed. And we talked about this special anomaly called Bilatti's anomaly, where basically the page fault rate can go up in certain circumstances when you add more frames to your system, which is a really strange thing. And we'd like to avoid this bad behavior because it just kind of indicates that there's something about the policy that's not very good, that adding more frames can actually cause the fault rate to go up. That seems like a desirable thing to avoid. And we also talked about the optimal policy. The optimal policy always evicts the page furthest. Let me see if I can state this correctly. It's the page that is accessed furthest in the future is the one that is evicted from the current in-memory pool. If you always do this, you will minimize the page faults for executing a program. The only problem is it requires you to know the future. And so the way that we can simulate it is by recording a memory trace and then using the memory trace to determine what page of the in-memory pages is accessed furthest in the future. And so that's how we can use it in research. But in a practical system where we can't read the future, we really can't implement the optimal policy. So what we want to do is try to approximate the optimal policy in some way. And so we tend to use the past behavior of a program to predict the future behavior of a problem. I'm just laughing because I see in chat that this was a CS38 problem. It used to be something in CS24 as well. It's just super fun to experiment with, but I can see that it would be frustrating to students to encounter these things once or even more than once. You can't escape. So the policy that we tend to use for approximating the optimal policy is least recently used, or LRU. And you see least recently used appear in all kinds of discussions because it's sort of the simplest way of approximating the optimal policy. As I say on the slide, LRU is basically the optimal policy applied to the memory reference string in reverse, because that's the information we have, how, which page was accessed furthest in the past. So LRU does not exhibit this anomaly that we talked about, where you increase the number of available frames and the fault rate increases. So LRU doesn't do that. There's a couple of problems with LRU, though. One of them I mentioned on the slide, and we'll discuss right away. Another one we won't actually talk to until toward the end of this discussion. So LRU, as it stated, is difficult to implement mainly because hardware is really limited and unforgiving in these kinds of contexts. It turns out that it's really easy to implement LRU in a purely software-based system. So if you're talking about accessing open files for your file cache, if you're talking about accessing database pages in a database implementation, it's quite easy to implement LRU. But we're talking about a very high-speed, high-performance context, memory accesses, and the virtual memory system. And so basically, we never try to implement LRU. So we already said opt is too hard. We've got to approximate it by implementing LRU. Well, turns out LRU is also too hard, so we approximate LRU with other policies. And the one suggested in the Pintos assignment is clock. And so clock is a very popular policy in these systems just because of how simple it is to implement. Okay, LRU two approaches that you could use. One is to have some counter associated with every page that is currently in memory. So imagine your page table entries are expanded to have another field in them that is a counter. And so the MMU has to now update this additional detail of when was the last time that each page was actually accessed. Okay, so the problem is the page directory is stored in memory, and now we're generating memory accesses for page accesses in our page table. So this is no good. We're already slowing things down a little bit. But at the very least, that is constant time, because when you have to pick a page for eviction, the only way you can really do that is to iterate across all the page table entries in the entire system to find the entry with the oldest counter value. And so that's the part that sucks, is that we actually have to scan through all the page table entries to try to find the one that was accessed furthest in the past. So this is gross. We desire not to do this because of the obvious overhead of eviction. The other option is to maintain all pages in a queue. And basically what we do somehow in the MMU is we track page accesses, and when a page is accessed, we move it to the back of this queue that we maintain. Okay? And you have to do this on every page access. When you have to evict a page, you just choose the one on the front of the queue. Well, that's not so bad. That seems like a pretty easy way to do it. And as I see on the slide, this is also unappealing, but in different ways. Eviction is now super fast, but every time you do a memory access, you have this overhead of updating this queue from hardware. At least everything is constant time now, at least, but everything becomes slower because we basically have to update this this memory access queue on a consistent basis. Okay, so these are the reasons why we generally don't implement LRU in these hardware memory, how shall I say, memory management units for supporting virtual memory systems. So there you go. So what we do instead is we approximate LRU, and we do this using a couple of bits that the memory management unit will update for us. Now, when I say the MMU updates them for us, when you look at page table entries, you'll notice they have a number of bits. We already talked about valid, or IA32 calls it present. It means that the mapping is valid. We also have accessed, which just means that the some part of the page has been accessed since the last time we checked or whatever. And then you have a dirty bit, which just means that there was an access that was also a write to the page. Now the MMU only sets these bits. It only sets them to 1. It never clears them. And it's up to the kernel to decide when to clear these bits in the page table entries. And so this is a way that the kernel can keep track of whether a page has been accessed since a given point in time in the past. So we can just go through, scan all the page table entries and check the access bits and see if something has been accessed. So you can imagine we do this with a hardware timer. We set a timer interrupt, and on a periodic interval, we go in and scan through all the page tables, all the page table entries, and see what has been accessed or what is dirty. And then we can make paging decisions based on that information. Now, not frequently used is an example. It's also abbreviated NFU. So all of these things are abbreviated in rather uncreative manners. We just use the acronym for the policy a lot of times. So NFU basically maintains a counter for every page. And that counter is simply incremented on a periodic basis if the page's access bit has been set. Okay, so we scan through all the pages on an interrupt. Maybe it happens once a second. Maybe it happens once on a quarter of a second. We scan through all the pages, and if the access bit is 1, we bump the counter. If it's also set to 1, we just clear the access bit for next time. and then we go through. And so then we can make a decision. Whoever's counter is low is clearly not frequently used, and so we just go ahead and evict that page, and that's how we make a decision with not frequently used. Now, it turns out that not frequently used is kind of a horrible policy. I've implemented this policy for virtual memory systems, and it makes terrible decisions, because you can have a situation where a page is accessed extremely heavily at the start of a program's execution, and so now the counter is really high, and then it never gets accessed again because the program just doesn't need it anymore, and that page is just going to sit in memory because it's going to have to take time for other pages' access counts to get above that page's count. So not frequently used is kind of lame. And you'll notice that the problem with this policy is that it considers frequency of access, not recency of access. And you can imagine that a good policy is going to probably consider both recency and frequency of access in some nice balanced manner in order to make good decisions. And NFU is a great example of a policy that only considers one of those things, and therefore it's terrible. So it's good in some very limited circumstances, but most of the time people don't use it because NFU is just terrible. So the reason why I like to present NFU is because we can make a few little tweaks to the policy, and we can get another policy that works amazingly well. And aging is an example of a memory, page replacement policy that works incredibly well in practice with a very little amount of overhead. So we still maintain a value for every page that's in memory. It's B bits, so B is the width of the age that we maintain. And so what happens is the access bit for every page is shifted into the topmost bit of this value we maintain for each page. Okay, so we shift all the other bits to the right. The bottommost bit falls off the end of the age, and we put the new topmost bit becomes the current access bit for the page, and then the access bit is set to 0 if it's 1. Okay, so the age value will be some combination of recency and frequency, because the topmost bit is also the most significant bit. So that's going to increase the value of the age by a lot. And as it shifts to the right, it will have a smaller and smaller impact on the age value for the page. So if we have a page that's accessed a lot, then it's going to have a lot of those B bits set to 1. And if it's got very few accesses, then very few of those bits will be 1. And as they shift right, the age is going to drop, precipitously. And so we can use that to select a page to evict. Okay, so I have some pictures because I love this policy so much. It's one of my absolute favorite policies. I've implemented this as well, and it makes really good decisions. So the arrows are timer interrupt ticks. And so this is where, you can look at the memory reference string. I haven't eliminated duplicates just because we want to actually consider proper passage of time. And so the page table is scanned, and we look for pages that have been accessed, and we, shift 1 in as the top bit. Otherwise, we shift 0 in as the top bit. So this is the this little guy right here is what the access bits will be for the page since the last timer tick. And so we end up with something like this. You can see pages 1 and 2 and 5 and 6 all have a 1, and 7 have a 1 for the topmost bit of the age, and therefore have the top values. And if we needed to make an eviction decision, we could just pick a page with a lower bit. Now you can see that as time goes on, we have another timer tick, and given the page accesses that occurred since a previous tick, we have 1, 5, and 7 have a 1 bit for the access. And so we shift that in, and you can see now that the aging policy is starting to distinguish between pages. We have another timer tick that occurs. Now it's 1, 2, 3, 4, and 6. And so you can see how pages ages start to adjust based on the axes and so forth. And so you can see that if you needed to make an eviction decision, that you could just pick the page with the lowest age or a page with the lowest age, and then you'd have a pretty good likelihood that it isn't being used very heavily, whereas ones with higher ages are much more likely to be used. Okay, any questions about that? I will mention, as an aside, I'm so excited for you all because you're probably like freaking out over implementing virtual memory for Pintos. The Pintos Virtual Memory Lab is, to be honest, kind of the simplest version of virtual memory you could possibly implement. It may not feel that way, but I want you to know that it is true. When you implement the page replacement policy, you don't have to worry about timer ticks. Timer ticks are not something you have to think about in the virtual memory eviction policy. And that simplifies your life because now you don't have to worry about something interrupting something else or yet another thing interrupting other things. So you don't have to worry about a timer tick. You can do it if you want. If you are already like mostly done with virtual memory and you're like, oh, I want to do something fun, try implementing aging. But in general, the recommendation is to use clock, and clock does not actually require timer ticks, which is weird given the name clock, but you can just advance the clock hand. Okay, let's see. Main difference between aging and LRU is aging has very low resolution on the information it considers. So you frequently saw in the example I just showed you that you have multiple pages with the same age. Aging doesn't distinguish between them. LRU would be able to. Also, if you have two pages with a value of 0, which means not accessed recently or frequently, then LRU would be able to distinguish between them, but aging does not know. So it's an approximation. That's what we really mean by this. And the interesting thing about aging is it does very well with a very small number of bits allocated per page in memory. And I actually did some experiments with this. And in the program that I wrote that implemented aging, I had 8 bits of age, 16 bits of age, and 32 bits of age. And the 8-bit aging policy was the best as far as minimizing faults. So it's quite an interesting little mechanism, and it's very popular because of its lightweight implementation, and also its seemingly quite good decision-making capabilities as far as virtual memory paging is concerned. Okay, so that's a fun one of my favorites. There are a lot of other ones that use the access bit and also sometimes the dirty bit. So one thing you can do with FIFO, we talked about FIFO last time. FIFO is terrible because it doesn't really consider recency or frequency at all. All it really considers is the time of the first access. You know, we order pages on the time of the first access. So what we can do is tweak FIFO to make it a little bit more intelligent. And so what we'll do is when we want to evict a page for FIFO, we will look at the page's access bit. If the access bit is 1, then we say, you know what? You are actually used in the time that you've been in the queue. So we'll go ahead and clear your access bit and move you to the back of the queue. So no shock, it's called second chance because of that. Because if you've been accessed, you get a second chance. You go back to the back of the line. If you haven't been accessed, you get evicted, and that's just that. So pretty simple tweak, and it turns out that this ain't so bad. In fact, second chance is exactly what the clock policy is, but just with different implementation details. So like I say on the slide, you consider the page at the front. If the page's access bit is 1, you clear it and move it to the back. Otherwise, you evict the page at the front. And so you can ask questions like, well, what if all the pages have been accessed in the time that they've been in the queue? Well, that's fine, second chance just in that scenario reverts to the behavior of FIFO, which isn't great, but that's what it does. Okay, so it's pretty simple enough. And so not so bad. Second chance is a nice little tweak to a otherwise naive approach that makes it a little bit more capable and a little bit more sophisticated. Okay, let's see. Clock. Now, clock is the one that I believe is recommended by the Pintos implementation, the Pintos assignment write-up. And clock is basically just the second chance policy, but with a cleaner and more efficient implementation. Because you don't maintain that actual FIFO, you just have a clock hand that sort of is the front of your queue. So you maintain the pages in a circular queue, and you have a clock hand that points to the next page that you're considering for eviction. And so when it's time to evict a page, you look at the clock hand, you look at that page, and you look at its access bit. And you say, is your access bit 1? Well, if so, you get excused, and the access bit is set to 0, and you advance the clock hand. And then you look at the next page. If it's been accessed, then you clear its access bit and you move the clock hand. Otherwise, if you find a page that hasn't been accessed, you go ahead and use that page as your eviction candidate, okay? And so you can imagine this wraps around, and if you have a situation where all the pages have been accessed, then it just reverts to FIFO, okay? Yeah, and so clock is great because you're not doing linked list crap. You're just traversing an array of pages, page frames. Now, I want you to think about this because some of you are already thinking about your frame table and that kind of stuff. And I've mentioned that the frame table is the thing that your virtual memory system will use to make eviction choices. So think about how you can build this. You have an array of frame table entries. And initially, and we've talked about this with some of you, you just grab all the available user pool pages and stuff them in the frame table. And you might think about, well, how would my frame table allocation work? Well, it can work the same way that eviction might work. You start with an index of the next frame to allocate, and initially that'll be 0, right? And you say, oh, this is unused? Here you go. I'm going to go ahead and hand it out, and then I'll just bump the index of the next frame to consider, okay? And then you just keep doing that. Now, initially, you may not have eviction. Remember, that's one of the suggestions of the implementation order. Get allocation working and get some things passing, and then worry about doing eviction. Well, the nice thing about eviction is you can basically use that same index to implement your clock hand. So you hit the end of your frame table, just wrap it around. And when you're going through and trying to find an available frame to evict the contents of, you can say, well, if it's unused, hand it back immediately. That's an easy one. If it's in use and not pinned, then consider the access bit. And, if the access bit is 1, clear it and advance the clock hand. If it's, obviously, if it's accessed, or let's say if it's pinned, you just advance the clock hand always, and you just wrap around that index pointer, that index value at the end of your frame table and go back to the front. And voila, right? Now you have a clock replacement policy implemented, and it just uses all this machinery. You don't have to do any crappy linked list manipulation. And as far as I'm aware, you completely satisfy the requirements of the assignment. So nice and simple way of doing it. You don't even need an interrupt handler. You just, do that basic thing. Okay, so I hope that helps. I'm not going to spend too much more time talking about this because we have other stuff to talk about in the discussion, but you can hang out afterward if you have questions. And we will be reviewing all of this stuff next time as we go through the Pintos design guidance. But this is why clock is super nice, and we recommend it. Okay. Not recently used. So this is a very simple policy that basically just categorizes pages based on the value of the accessed and dirty bits. And we can go through with a timer interrupt to update our information that we have and also clear the access bits for pages. So we have these 4 classifications, because if you think you've got accessed and dirty, so that means that you can fall into one of 4 classes. Class 0 is not accessed and not dirty. Class 1 is not accessed and dirty. And remember, this can happen if the timer interrupt goes off and some access bit was set to 0, but it was also a dirty page. So we can have that situation. Class 2 is accessed and not dirty, and Class 3 is both accessed and dirty. Now, if you were to look at these and try to figure out which page of which classification would I prefer to evict? And you'd probably say, well, I'd like to not have to evict the page and write it back somewhere. So I'd like it to not be dirty. And also, if it's not accessed, that seems like a good idea. So you'd probably prefer to pick from class 0 if there are any in there. Now, maybe you have to find something, and so you say, well, to avoid messing up program execution performance, I'd like to evict something that hasn't been accessed recently, but if it's dirty, then I still have to write it out. I'll take the hit, and so forth. And so the way that NRU works is exactly this way. You choose a page from the lowest class that isn't empty. And that's where you choose a page from to evict. Okay? So, oops, lost track of my arrow keys. So basically, we're trying to choose a page that is the lowest cost to evict, if at all possible. Okay? Now, you can always extend these kinds of mechanisms, like have a background thing that goes through and looks at dirty pages and cleanses them by writing them to the backing store or writing them to the file that they're mapped from or whatever. And so you can take something like NRU and enhance it by incorporating other mechanisms to cleanse dirty pages and so forth. And so you frequently see that kind of a mechanism incorporated into virtual memory systems. Thankfully, not something, I don't believe this is something you have to implement for the virtual memory system. You have to implement it for the file system cache in the next project, but I don't believe you have to do it in the virtual memory system. So again, we're trying to keep this as simple as possible for you, because virtual memory is hard enough as it is, turns out. Okay, working set-based policies. What is a working set? Well, there's this special sort of term that you can use to consider the set of pages that a program is actually working with. And we call that the program's working set. The working set of a program is going to change over time as it accesses some data and then stops having to work with it, and maybe it moves on to accessing other data. So over time, the working set is slowly changing. And you can imagine that the working set may grow if there's a lot of data in memory to work with, or it may shrink if there's not much data to work with. And so we can try to design our paging policy to take the working set of a process into account. Okay? If we evict pages that are outside the working set, then there's a good chance that we won't generate faults by accidentally evicting something that the program is still working with. Like, that's the big issue with page replacement policies, is we don't want to generate unnecessary faults by evicting something the program was still trying to use. And so the working set policy that we're going to talk about tries to approximate the working set using some simple mechanisms. Okay? So here's how we do it. We have the memory reference string. We consider a certain point in time. In this case, it's T1. And we say, all right, we're going to try to guess the working set of a program by considering all the accesses up to a certain distance in the past. So that's what this tau represents. That's the size of the window that we're considering. Larger tau means that we're going to guess the working set is larger. If tau is very small, then we're going to guess that the working set is small, because obviously we only have a limited number of memory accesses to look at. Okay? So yeah, as I say here, you want to choose a tau that's large enough to capture the working set, but not so large that it overestimates it and not so small that it underestimates it. So at time t1, you can see that we have a working set of 1, 2, 5, 6, and 7. These are the page numbers. Some suspension of disbelief here. You all know that it's significantly more complex than that as you dive into the implementation. And so at a later time, t2, you look at t2 minus tau and you say, okay, well, now we have a different working set, 1, 2, 3, and 4, and we'd like to have a policy that will evict pages 5 through 7. Okay, so this is the idea. This is the premise. So we have a policy called WSClock. WS stands for working set. And WSClock is kind of a Frankenstein's monster of paging policies, all kind of smooshed together. So let's go through this and talk about how it works. We basically have a virtual clock for every process. So you notice already that this is kind of a per process policy. This is the way that we're describing this. And that'll become more important when we talk about page allocation policies on Monday. So you can imagine that you can do paging decisions on a per process basis or on a global basis. So we have a virtual clock, at least is the way we're stating it here right now, a virtual clock per process. And basically we can use that virtual clock to decide which one was accessed furthest in the past. Okay. So pages are kept in a circular queue, and each page also has a time of last use value associated with the page. And that's going to be taken from this virtual clock. Now, when we have a timer tick go off, remember this is on some, not every timer tick, because we don't want to do this every single timer tick, but maybe on a quarter-second basis or every 1 second, something like that. We scan through all the pages, and if the access bit for the page is 1, we update that time of last use value. We take it from the virtual time, okay? And then we clear the access bit. If the access bit is 0, we don't do anything for that page. So that time of last use is going to somehow reflect when we saw it accessed. Okay? Hopefully everybody's keeping up with this. So now we have the question of eviction. When we're trying to figure out eviction decisions, we have a clock hand again. So this is the clock part of WSClock. And if the access bit is 1, we say, well, it's definitely in the working set because it's been accessed since the last time the timer tick went off. Okay, so we just clear the access bit and go forward. Now that's the first part of this decision process. The next part of the decision process is, what if the access bit is 0? Well, we'd like to respect the working set of the program, so we look at the time of last use value. And if that time of last use value is within our window, within our tau of our current virtual time, then we ignore the page again. We don't actually evict that page because even though its access bit is 0, we're saying we still think it's in the working set. So you can see that this is just an extension of the clock policy to include this notion of a working set. If it's further in the past than tau and its access bit is 0, we say, you get to go away. Now we have 2 more possibilities, right? It may be a clean page, it may be a dirty page. And since we know that dirty pages are more expensive because we have to save the contents of the page somewhere before the frame is available for use, we will prefer the clean page over the dirty page. And so if we find a dirty page, we schedule the saving of the data. So we're taking it, we're cleansing it, we're turning it into a clean page, but that takes a lot of time. So we initiate the process and go on. If the page is clean, then we know there's no cost for eviction, so we go ahead and use that frame for the new page that we need to load. Okay, and so you'll see, this is LRU is making its little appearance here because we're biasing toward clean pages and trying to cleanse dirty pages along the way. All right, so I'm going to back up and ask a question. Because when I try to describe this, and this is a great example where a picture is worth 1,000 words, like you'd probably want to make a flow chart to keep track of all this. Okay, on eviction, I'm looking at a page. If its access bit is 1, set its access bit to 0 and go on. If the access bit is 0, consider the tau value and see if it's still in the window. If that's not the case, then is it clean? Is it dirty? And you're like, okay, this is complicated. And it is complicated. And that's kind of one of the things that I think is interesting about OS implementation, because this is definitely an example of a heuristic type policy. Some smart OS designer, or OS designers plural, sat down and said, let's cook up a policy. And they took multiple policies and kind of smushed them all together into this Franken policy, if you will, that has these different characteristics of it. And you have one parameter that you really need to tune. That's tau, right? So you have a single knob, which is kind of nice. Turn the knob one way, make tau large, you get certain behavior. Turn the knob the other way, make tau small, you get other behaviors. And you sort of have to figure out this one parameter, but at least it's only one parameter. And I think this is a great example because there are a lot of situations in systems implementation where you do just come up with a Franken policy, the best Franken policy you can, and you just try to see how well it could work. I would almost argue that the Linux epic-based queue scheduler, multi-level queue scheduler, is a very similar example of that. But of course, you know that they abandoned it because it was too difficult to tune. So you do run into this quite a bit in systems, and that's why this was a policy that was used in a particular operating system, and I probably wouldn't choose it because you all know I love aging. And if I didn't choose aging, I would probably use one of the policies I'll talk about at the end of today. But, you know, it's interesting that there are these kinds of policies rather frequently in OS implementation and other systems. So I wanted you to see it. Okay, a few other little details. What if we traverse all pages while looking for a victim? Well, we have one possibility, which is that we came across at least one dirty page that was outside of anybody's working set. So a write was scheduled, and eventually that write will complete, and we will eventually come back and it will be clean. And so then we can use it. So that's one possibility. The other possibility is sadness, which is that no writes were scheduled. And if we have a situation where no writes were scheduled, then we're in sadness land. And so we just go ahead and pick a clean page and evict it. Now, I suppose you could just pick one that was furthest in the past in the working set, because they're not all going to be accessed at exactly the same time. So you may still be able to differentiate. But you can see that WSClock kind of gets into trouble when you have heavy memory pressure. That's what we call it, when there's a lot of memory accesses going and we have to make some unpleasant decisions about, you know, where it's like a Sophie's choice. We don't really have a great decision here. Okay, so that's enough about WSClock. Let's pretend we never talked about it. Okay, a few other details to keep in mind of how modern virtual memory systems work. One of the very common approaches, it pays off so well that I'm pretty sure that every modern operating system does this. They use page buffering, which is basically figure out how to identify pages that are candidates for eviction, but don't actually do the eviction process right away. And so you kind of build up this bank of good candidate virtual pages that you could choose when you need to do an eviction. Okay, and so that's what I mean here when I say a pool of free page frames. Wow, say that 5 times fast. Or a pool of candidate pages. That's another way that this can be expressed. And so those are ones that you would use if a fault occurs to resolve the fault very quickly. And like I said, this is so good of an approach that it's very popular in modern operating systems. Don't do it for Pintos. You don't need to. But this is what Linux does, and this is what Mac OS does, and this is what Windows does. So what the OS does is it periodically looks for pages that may be good ones to evict, and it reclaims them, but it doesn't actually go through the whole process of eviction. It starts maintaining them in a pool. And in fact, it has two pools because the page may be clean or the page may be dirty. And so it puts clean pages into a pool of candidates for eviction. Because remember, since it's clean, we don't have to write it back anywhere. So we can just handle that fault immediately. Dirty pages are put into another pool, which is known to be a pool of dirty pages that are candidates for eviction. And the OS has some background operation that will go through and slowly but surely cleanse those pages by writing them back to where they need to go. Okay? Once they're clean, they're put into the clean page pool. And so you can see how we have this background mechanism to sort of prepare pages for eviction cheaply so that we can handle faults fast. Okay, so the free page frame pool can be used to reverse. Oh, this is what's so cool, right? Because you may have a paging policy that says, you know what, I'm picking these 5 pages as candidates. But maybe some of those pages are still in use by some program. And so it's in the pool, but it still has its old contents. And so what can happen is if a fault occurs, and it's a fault for a page that's actually in this pool, the kernel can just be like, whoops, that was a bad decision. And it can pull the page out of the candidate pool and put it back into the process where it needs to be stowed away, so it gets remapped back into the process's virtual address space. And so this is really cool because we just handled a fault to identify that a paging decision was bad, but really the only expense there is trapping back into the kernel, remapping the page back into the page table for the process, and then getting back to the process. So this allows us to have a simple policy that is allowed to make bad decisions, and we can revert some of those bad decisions when we discover that they were indeed bad. Very common approach in operating system implementation now. Okay, this is an older school example I'll just mention quickly. There was a processor called the VAX, which hopefully none of you have ever had to work on. When I came to Caltech as an undergrad, the first computer that I worked on as work study in full time, it was in the Caltech seismology lab, was a VAX. And it ran this operating system called VMS. And the hardware had a bug where the access bit wouldn't be updated correctly. So the MMU had a bug in it, a hardware bug. So VMS didn't have access to depend on, so it just used a FIFO policy. So when I load the page, when I get a fault, I'll load it, I'll put it into a queue, and then he used page buffering to give pages the second chance. So that's how VMS solved this hardware deficiency that existed in certain VAX processors. So like I say, if the FIFO policy specified a page to be reclaimed that was still in use, then you would just get a page fault when the page was accessed, and then VMS would go and pull it back out of the page pool and put it back into the process. So pretty clever technique, I think, to work around a hardware failure. Okay, another crazy thing, because, I've waved and gesticulated my iPhone at all of you multiple times in this class because, hey, ARM processors are everywhere. This is probably, this is an iPhone 12, so it's probably Apple's design of processor or whatever. I don't know if they use ARM as the architecture for that. But older phones, definitely, ARM is ubiquitous. Well, it turns out that some MMUs, let me see because I don't want to get distracted from the new topic if I need to answer a question about an older topic. Page buffering, the page isn't technically evicted, so how does the faulting process immediately have a frame to use? Well, the faulting process, there's two ways that I can interpret your question. The faulting process may fault on a page that is not in memory at all, not in the page pool, but it's on swap or something like that. Remember that eviction is no longer sort of just in time, but the eviction mechanism is periodically identifying candidates for eviction. So that's what populates the page pools. And so when you get a fault, the fault handler can actually go and look at the clean page pool and just pick one out of there because it knows it will be basically free to reinitialize that frame to be inserted into the new processes page table. So hopefully that answers that question. If it happens that the page fault was on a page that's in the clean page pool or the dirty page pool, then it's also cheap because you just say, oh, I made a mistake, and you pull that out. But I think the key detail for your question is that eviction is no longer just in time, but it's more aggressive and preemptive in the sense of going through and identifying candidates to put into these page pools, as opposed to just, I need a page right now, and so it goes and runs. So hopefully that answers that question. Okay. OS emulation, yeah. ARM processors have an MMU, but the MMU doesn't implement the accessed or the dirty bits. And so it's like, how in the world do I make paging decisions if I don't have an access bit and a dirty bit? And this is a problem that Linux has to solve because Android phones run Linux and they run on systems without accessed and dirty bits in the MMUs. So basically, there are clever ways of figuring this out. Basically, Linux on ARM uses two page tables. So you have the page table and the supplemental page table. And what happens is when a page is allocated to a process, the page is marked read-only. Now, if only reads occur against that page, no problemo. But if somebody tries to write to the page, you get a protection fault. And the Linux protection fault handler goes in and says, somebody's writing to this page, and it sets the dirty bit to 1. And then it changes the permissions to be read-write, and then the access succeeds. Similarly, you can emulate the access bit by periodically going through and clearing the page table entry valid bits for all the pages in memory. And then as pages are accessed, you'll get a fault. You'll get a page fault. And you go in and you say, this page is present, but now we know it's also been accessed. So you can set the accessed bit for that page to know that a read occurred on it. So this is a really clever mechanism, and I wanted to tell you about it because it's just like, you can have very limited and simplistic hardware, and a lot of times you can work around the simplicity of the hardware using various software techniques. So it's a really amazing little thing. Okay, I don't want to geek out about that too much or else I'll run out of time. There's one more thing I want to tell you about. There's a real issue with plain Jane LRU. As I have on the slide, LRUK means what was the time of the most recent kth access. And plain Jane LRU would be LRU1, which means when was the last time it was accessed once, at least. So LRU2 already is a huge improvement over LRU1. And the reason why is because LRU is susceptible to memory scans. When you have a program that loads a bunch of data into memory and then scans all of it once and then never accesses it again, now LRU thinks that all of those pages are super important because they've been accessed super recently. But the reality is the program will not access those pages again, and so you have to wait for the pager to realize, oh, those things aren't used anymore, and then finally it can get rid of them. This is pretty terrible, especially because it's super common in database systems. Databases frequently load a bunch of data off disk, scan through it, and then don't access it again. And so LRUK policies oftentimes well outperform LRU1. And this gives rise to one of the coolest adaptive policies, and I'll just present it to you so that you can think about it. Currently, the patent is held by IBM, which is dissuading a lot of people from using it in open source software for understandable reasons, but you'll oftentimes hear it abbreviated ARC. So ARC has two LRU queues, and you can sort of think of it as in the middle, and on one side is LRU1, so L1, and so that means the page has only been accessed once. And so that is recency of access. Then you have another queue, which is L2, and this is I've been accessed at least twice. Okay, so that is frequency as well as recency. And you can imagine the L1 queue is going to reflect scans, and L2 is not going to reflect scans because it's been accessed at least twice. And so basically you have these two queues, and they have a top region and a bottom region. And the top region corresponds to pages that are in memory, and the bottom region is stuff that was in memory, but the policy decided to evict it. So you keep those entries there because you want to know if it was a good choice or not. Okay, that's why they're called ghost entries. It represents history, but the page is no longer in memory. And so what happens is when you have a fault and there's a ghost entry for the page that the fault occurred for, you tune the policy in the direction of the ghost entry. So you grow the L1 queue size, how much is kept in memory for L1. Or if you get a fault on a ghost entry on the L2 side, you grow the L2 queue and take away something from the L1 queue. So it shifts back and forth based on what faults hit ghost entries so that it can tune to the behavior of the programs that are running currently on the system. And ARC, it kicks LRU's ass so hard it's not even funny. So if you want to go look up ARC as a not just a body of governance at Caltech, but also a page replacement policy, you can see some of the research papers that show how incredibly well this performs. So it's just really neat. There's another one that I'll mention, which is called CAR. This is the open source friendly implementation of ARC. It's self-tuning, but it's kind of like a clock wheel, and then you have a hand that sort of tunes in different directions based on the way that the policy observes its decisions. Okay, that is plenty. I know that I'm keeping you guys a little late, so just be aware. Next time we'll talk about Pintos design guidance. I will see you next time.